Okay, we will start with the pre-lab lecture for the Grignard reactions. So this will be the first experiment in a series that we will be looking at in the carbonyls, and then we wrap up the semester with the carbonyls. We start with the simple Grignard to form a carboxylic acid. So you know this really well, but I thought it's kind of a good place to get started. The Grignards are organomagnesium compounds. They're organometallics. They're organomagnesium reagents. And the general formula is RMGX. R can be, there's a lot of variations there. You can have alkyls, you can have really bulky tertiary butyls, you can have small methyls, aryls, you can have benzenes with a variety of substituents, electron donating, electron withdrawing, alkenyl, which means you can have double bonded like vinyl, alkynyl, which means you can have a triple bonded groups as well. So it'll take a lot of different groups. X is a halogen, so it's not restricted to the best leaving group or anything because a halogen doesn't leave like a leaving group, which means you can use a fluorine as well as, just as good as an iodine. Now you can represent a Grignard this way, where R takes on a delta minus and the metal magnesium takes on a delta plus. But I know a lot of you like to break it down and write it like that. With R minus, the carbon is going to have a dual function. It can be a nucleophile as well as a base. In the spectrum of the simple organometallic reagents, the organolithium has the greatest polarity difference, and so it's going to be the most reactive. The Grignards fall somewhere in the middle, and then towards the end are the Gilman reagents. But this is not the complete spectrum. If you take the organo-palladium, organo-zinc, they are even less reactive than the organocuprates, but they react in a different sort of way. So our Grignards are kind of less reactive than the organolithiums, but more reactive than the Gilmans. Now, if you read the procedure already, you know that you will take bromobenzene and you will add small pieces of magnesium in dry ether. Dry is also referred to as anhydrous, so no water. It's conducted in glassware that are also flame dried or oven dried for a good 2 hours at least. That means all water is removed. This reaction is called an insertion reaction, where magnesium, which is divalent, inserts itself between the organic fragment, which is the phenyl group, and the bromine. This is your Grignard reagent. The actual name is phenyl magnesium bromide. Now, this is typically prepared in situ, which means it's prepared on site and used right away. There's a reason for that. So if we take this particular reagent, and let me go ahead and write the complete structure here. And then what I like to do is break it down, and write it as C6H5 minus MgBr plus. If you don't approve of it or don't think it's that ionic, you still like to keep the covalency of the bond, you can certainly go with this. Let's say you have a little bit of moisture. So what you have is a delta minus and a delta plus. The C6H5 minus will grab a proton and it'll become C6H6. So you really form benzene. And then, of course, you're going to get the other, inorganic salt. So if you have any amount of moisture, the Grignard will be destroyed. The Grignard will react with moisture. And that's why you want to really perform this formation of the Grignard in anhydrous conditions. You don't want to store it because storing is always a risk. You're going to get some moisture inside. That's why you want to prepare it in situ and use it right away. You're going to add this to dry ice. Dry ice is solid carbon dioxide, and that's what you're going to add it to. Now, when you take the structure of dry ice, the carbon in the middle looks very much like your ketone carbon. So this is going to be delta minus, delta plus. The molecule itself is nonpolar, but it has polar bonds. It is a linear molecule. The dipole moment will cancel. You've read a lot about it. So the linearity, the shape of the molecule renders it nonpolar, but the molecule itself has polar bonds. And here you can see the covalency of this is maintained. If you don't want to maintain that, you can use a negative charge on the carbon and attack it. this negative charge is not on the hydrogen. It's actually on the carbon, but you write it like that, attack it on the carbon, and then you polarize the double bond towards oxygen, and this will be your product. So what you're getting is a carboxylate salt. So in simplistic terms, if you acidify the solution, you'll get your benzoic acid. Okay, fairly simple mechanism, mechanistically very simple, although I have a slide there. It's pretty straightforward. You're just going to have this tack, the carbon, make it O minus. So we have done this before. It's going to be like this. And then, all this means is you add a little acid, and then you get your benzoic acid. So one issue with dry ice is it sublimes, but that also makes it great, because what you can do is you can use your Grignard as a limiting reactant, which means you can use your bromobenzene as a limiting reactant. You can use a slight excess of magnesium, and you can use an excess of carbon dioxide. So any excess magnesium can be easily picked with a pair of tweezers. Literally, students just pick it with a pair of tweezers and remove it, because they can see the solid magnesium. And after some time, the carbon dioxide, the excess just sublimes and goes away. So it's such a clean reaction, can give you benzoic acid as the only major product, only organic product. But what I want to show you is a section called workup and isolation. And I prepared these PowerPoints based on questions asked in your post-lab. And there is a question directed to the mechanism. There's also a question directed to workup and isolation. You're asked to write this workup in a format that's different than what's given in LabFlow. So this is what is given in LabFlow. We need to convert it into a different format, and we can use a flowchart format to do that. Now, what is workup and isolation? So what happens is, this is what you get. And very simplistic terms, we're just saying add acid and you will get benzoic acid. But that's not exactly how it happens in the lab. So this is what you have. You have the carboxylate salt. So this is your PHCO2 minus MgBr plus. You have excess magnesium. And this is if some of the Grignard reacted with water. Yeah, you're being really careful. But remember, you may just swap to the balance area, pick up the reagent, wait, and come. By the time some moisture can get into your round bottom flask, and some of the Grignard can react and form benzene, right? I told you how that's formed. Now that benzene can combine. So this is if some Grignard reacts with trace amounts of water. I'm not saying you'll dump a whole lot of water intentionally into your system, but if there is moisture, some of the Grignard is going to react and form some benzene, or the benzene can react with itself and form some dimers. So that's possible. So this is the kind of the mess you're going to have. This is going to look like a gooey solid, very sticky solid with some magnesiums and whatnot. So what you will do is add ether. This ether is methyl tertiary butyl ether. It doesn't have to be so complicated. You can use simple ethers, but this is the ether that's used by LabFlow. It doesn't have to be that. You can use something like diethyl ether. So you can have two ethyl groups. You can certainly do that. That's a simple ether that we can use. You're adding some HCl, you're adding some water. There's a reason to do all of that. So let's take a look at the reasons. So you're adding some HCl. So you got some excess unreacted magnesium. You will add some HCl, so that will become MgCl2 plus hydrogen, hydrogen gas. So when you add HCl, you'll see some bubbling. If you have some big chunks of magnesium, you can just use tweezers and remove it. If you have small amounts, you add HCl and take care of it. Okay, magnesium chloride will dissolve in water. So all of this will go into what is called, this of course escapes. Well, it's a gas that escapes. This will go into the water medium called the aqueous phase. All right. And then you're going to add some ether so that it will take any of the organic compounds into it. So we're going to get two layers. We're going to get the water layer. The water layer is going to have the HCl. It's going to have any of the magnesium salts and all that. This is your aqueous layer. So we need to convert this into a flow chart. So we want to have this information. All right. The top layer is organic layer. The difference is based on densities. The organic layer is going to have some of the benzoic acid, any of the side product, any of the benzene that is formed, and then it's going to have all your MTBE and all of that. You pour it into a separatory funnel, you're going to get a lower aqueous layer, and then you're going to get an upper organic layer. So if you remember the separatory funnel, we used it last semester, goes online, and you can separate the layers based on densities, and you can open the tap and it can bring the bottom layer down. Okay, that's what you do. You drain the lower aqueous layer. We don't want the lower aqueous layer. You set it aside. Now your top layer, you're going to have your benzoic acid, which is your product, any of the side product. This is going to be a small amount. This is your solvent. You're going to add 5% sodium hydroxide. So what happens there? So let's take a look at that reaction, because we will be converting all of this into a flow chart. You're going to add 5% sodium hydroxide. This is not an unfamiliar reaction for you. Acid plus base gives you salt and water. So that's what you're going to get. Okay. So now when you add 5% sodium hydroxide, you're again going to get a lower aqueous layer and an upper organic layer. Okay. So your lower layer is now going to contain the sodium salt of benzoate. The reason for that is this is ionic. It's going to be soluble in water. Your upper layer now contains the solvent as well as a side product. So you can see there's a lot of separation that happens. Now you take that, you drain the lower layer. We don't, right? Which is where your product is. Now you want to keep in mind, this lower layer is important. You want to drain it. The upper layer is what we don't want. To the lower layer, you're going to add HCl, which means you're going to add HCl to this. You'll get sodium chloride, which is a side product, and you recover your benzoic acid. Okay. So it's a little tricky where one time you don't want your lower layer, the other time you want it. So you're asked to write this entire separation in a different format. The format that we can use is a flow chart. So we're going to start with what we have initially here and build a flow chart. So what I want to do is go ahead and write this down. I'm going to write the ions because it'll make it easier. Then you have excess magnesium. Then you have your side product, which is a little bit of benzene. It can also be benzene dimer. These are all your side products, both of them. This is your main product. This is your main organic product from which you're going to get your benzoic acid. Today's goal is to react Grignard with carbon dioxide to form benzoic acid. Unfortunately, it's contaminated with a lot of other things. So what we're going to do now is we'll build a flow chart. So we'll have a long arrow. We'll keep it simple. We don't have to write MTBE. We can just say add ether, solvent, add HCl, add water. So this is organic solvent. So keep that in mind. It's not going to mix with water. So you're going to get two layers, aqueous and organic. So we're going to say aqueous layer, organic layer. So in the aqueous layer, what's going to happen is your magnesium is going to react with HCl to form MgCl2. Okay. And then your MgBr is going to combine with HCl to form MgClBr. All of these guys are going to be there. All right. You're going to have some unreacted HCl, which will also go into the water layer. Of course, it's going to have water. Your organic layer, the CO2 minus, is going to grab the proton because this is H plus Cl minus. The minus charge is going to grab the proton and this will be your benzoic acid. So if you don't want to write pH, you can write this as C6H5. I'll leave that to you. Apart from that, you're going to have ether. So let me know if you have any questions so far. Now this one you're going to discard, right? So what I like to do is this. You can write discard there, that's fine. Or you could say separate and discard. I don't like to say separate because my flowchart separates it. So I'll just say discard. I don't have anything of value here. So this is the aqueous layer that goes away. So now I'm only concerned about my organic layer. Now to my organic layer, I'm going to add sodium hydroxide. You don't have to specify the percentage. I know it says 5%, but that means it's dilute. That's what it means. Concentrated sodium hydroxide is 33%, but we don't have to say that. Now remember, this is organic layer, this is ether. Sodium hydroxide is a solution in water. Water and organic don't mix, so you're going to get two layers. Aqueous layer, organic layer. Your aqueous layer is going to react. So the benzoic acid is going to react with sodium hydroxide to form this. It's going to form water. All you're going to have here is ether. Now, you're also going to have, I forgot to say that you're also going to have benzene. You're going to have these. So all of this will go here. I forgot about those side products. You need to write those. Because you had those, right? You had them right there. Those need to go to the organic layer, and now they go there. Now, this one I don't need, so discard. This is where my product is. So this is the aqueous layer I need. Be careful, because the other aqueous layer you didn't need. You discarded, you needed the organic layer. Now you don't need the organic layer, you need the aqueous layer. To this, I'm going to add HCl. So what I'm going to get is C6H5COH plus NaCl. This will be a solid. This will stay dissolved in water. Now what you do is suction filter and separate it out. So you will get only the solid benzoic acid. So this is going to be how you're going to explain. Unless you want to write all of this in sentences, I think it'll be a lot easier for you to build a flow chart. This is typically what we use in our workup in organic lab after lab after lab. You don't, things are not really cozy. You don't just form your organic product. It's contaminated with a lot of other things. So this is called workup and isolation, where you work it up and you isolate your desired product. So here you've isolated it. So let me know, it's kind of a small font, but I brought it all on the screen. Let me know if you have any questions, and this should take care of one of your post-lab questions. I hope all of this makes sense. This is after the reaction is done. This flow chart is after the reaction. The reaction is over, it's formed your product, but unfortunately, it's not in the state you want it to be. It's contaminated. We are just separating it out, okay? Now, another section of your lab flow is calculations. So you're asked to pick a value in the given range. So what you have here is vial cap and bromobenzene, then you have the mass in the vial cap. So if I call this 1, I call this 2, 1 minus 2 will give you the mass of bromobenzene. Moles of bromobenzene will be this value 3, so we'll call that 3. So you know how to calculate the moles. So it'll be 3 grams. It's not 3 grams, it's this value 3. So please, you know what, let's not do this. So we'll say A, B, and then this will be A minus B. So we'll go A minus B grams times 1 mole divided by molar mass of bromobenzene. So that is C6H5 be, or I did not look it up. I just remembered that I didn't look this up. So you can look up the molar mass of bromobenzene, or I can just do that right now. It's 157.02 grams. So you need that. And then here is mass of magnesium used. So you will calculate the moles of magnesium. So that'll be C times 1 mole divided by magnesium, which I think is something like 24 grams. I'm not 24 point something. Okay, so that's a molar mass of magnesium. You want to get that. So that'll actually give you, so what you want to do is this, you want to look, you know, where I'm going for, you want to find out whether bromobenzene or magnesium is a limiting reactant. I'm really hoping bromobenzene is the limiting reactant because we are using hydrochloric acid to remove the excess magnesium. It'll be kind of a joke if magnesium is a limiting reactant because we are adding HCl for no reason then. So I really hope bromobenzene is our limiting reactant. So once you get the limiting reactant, you're going to calculate the theoretical yield, and it's a 1-to-1 ratio. So what you're going to do is mass of limiting reactant, whatever that is. I'm really hoping that is bromobenzene. Okay, so that's going to be in grams. And then you're going to go ahead and convert it. So you've already done that. So if you like to go for theoretical yield a little bit differently this time, you can just say number of moles of limiting reactant times, it's a 1-to-1 ratio. So 1 mole of benzoic acid, 1 mole of limiting reactant. And then you can cancel out the benzoic acid. So you do need the molar mass of benzoic acid. So I'll go ahead and get that. So you must show these calculations. You want to upload a page or something. So this one, I'm expecting it to be bromobenzene. Hopefully it is. But in theory, you have to find out whether it's bromobenzene or magnesium. All right. So that'll give you the theoretical yield from which you're going to get the percent yield. So let me know if you have any questions. I mean, you've done this a few times. I don't think you're going to have any issues, but if something doesn't look familiar or you have questions, feel free to ask me. Oh, letter C, I just made those up. C is the mass of magnesium used so that I can write C here. I don't know what you're going to choose. You guys can choose what you want. You're given a range 0.450 to 0.550. So choose something. Yeah, I just called it C. So you'll take that value that you've chosen times 1 mole and then molar mass of magnesium. It's actually 24.31 grams. That's the exact number. So that is atomic weight or molar mass of magnesium, whichever way you want to look at it. Doesn't matter. Now, once you've done with all of that, benzoic acid melting point, you're asked to look up the expected. It's typically 120 to 122. So I'm just giving you the melting point of benzoic acid. That's a literature value. You want it in degree Celsius. Okay, so provide a reasonable melting point for a product that is not completely pure. So what I'm looking for is lower than 120. You want to exaggerate. So you want to go really low, like 80 or something. Don't go 115 because that doesn't happen. We are at a distinct disadvantage of not having done this in the lab. So what really happens is when it's impure, it drops down tremendously. It's not like 110 or something. It'll drop to 80 or something. No student can miss it. And then I want a really broad range. Your broad range is not 5 degrees or 10 degrees. So you don't have to give this, but it'll be something ridiculous like this. You know, you just can't. And sometimes it'll start at 80 and it'll go on forever. This, students may not even wait to get the final range because it just keeps going on. It's a really broad range. So that's what I want to, when students don't give that, that's really not their fault because they haven't experienced this via lab. So it's really lower than 120. Drop it really low and exaggerate it. Give a really broad range because you're asked to come up with something that's not completely pure. So that should take care of a bulk of your lab flow, except one question. So before I go to the infrared question, anything else here? So what I did here is I took the storing organic compound. I always like to take, in the labs, I like to run the storing organic compound. So we make it available in Canvas. Then every student will run the IR of that product. So if benzoic acid is what they form, they'll run the IR of the product. I just don't like to run only the IR of the product. So this is the IR of benzoic acid that's given by LabFlow. So I use theirs. So this is IR benzoic acid. So I'm just going to go ahead and draw the structure here. But this one I got from SDBS, which is a database maintained by the Japanese. And this one, and it's open source, we can use it. So this is just bromobenzene, okay? So the key thing we are looking for is a major difference here. We are looking for the carbonyl group, which we see here. So you're asked three distinct things. So that's a carbonyl group. So I would say 1900, 1800, 1700 wave numbers. So that's the absence of carbonyl. Right. The next thing we are looking at is the carbon-oxygen bond, which is right here. So right here, that's 1250 wave numbers. That's a carbon-oxygen single bond. Again, you do not see that here. Then we are looking for the hydroxyl. The hydroxyl is kind of unique. It's going to, it's not going to be sharp at 3400, but instead it's going to kind of spread out. So it starts off like 3200 wave numbers, and then it goes pretty much, let's see, 29, 28, 20, so something like 2500 wave numbers. So it's a pretty broad stretch. It kind of covers your carbon hydrogens as well. So you're asked three distinct peaks. I would go with carbonyl as one distinct peak. I would definitely go with carbon oxygen, even though it's in the fingerprint region. I like the peak sometimes because it's a strong peak. Of course, it's kind of a clumsy region, but if you go looking for that peak in that region, you'll find it. It's not like looking for a needle in a haystack. It's pretty strong. That's what I mean. And then you got this hydroxyl peak. And a lot of students have asked me before why it's not a nice bell-shaped curve at 3400 like it would be for an alcohol. It is not so for the carboxylic acid because the carboxylic acid is very polar. And, you have this very popular concept, right? Resonance. So you have this polarity. And you have this resonance here, which makes this double bond, into a single bond and makes this single bond into a double bond. So it doesn't come shortly at 3400. So it kind of moves a little bit from 3200. And it's because it's very polar, it kind of sweeps a broader area. And it actually covers the carbon hydrogen peaks as well. So that's why it's kind of clumsy. So those are your three major peaks. I believe the question says three absorption bands. Anyway, we'll take a look at lab flow, but that should take care of that IR question. And you do not, definitely you see the absence of the hydroxyl peak. So even if you're not asked to compare the IR with the starting material, I always like to do that because you see a nice change. That's how you know your reaction has actually taken place. So I'm going to move to lab flow, but if you have any questions, as always, feel free to let me know. So select the type of reaction. You want to go with nucleophilic addition because this is nucleophilic addition. The nucleophile adds to the carbonyl. So write a balance equation for the formation of the Grignard reagent with the bromobenzene. All of that is available. This will be your balanced equation. So when you write a balanced equation, what you want to do is C6H5Br plus Mg, C6H5MgBr. If you want to write the structural equation, that's fine. That's also balanced. And then, see, I think it's the next equation. Write the balanced equation for benzoic acid from the Grignard reagent. Include all reagents and products, not solvents. So let's go to that. So what we are going to do here is write the next equation. That's going to be C6H5MgBr plus CO2 will be C6H5COO minus MgBr plus. That would be a balanced equation. Everything after that, adding HCl and all that, is not part of that reaction. It is actually going to be part of the workup. But if you want to write it, what you want to do is continue on. You want to add HCl. That'll be C6H5COH plus MgBrCl, and it'll still be balanced. It'll all be balanced. Okay, if you're comfortable getting to this final product, benzoic acid, keep in mind that this is part of workup and isolation. This is not really part of your reaction, but if you want to go to the final product, which is benzoic acid, you can certainly do that, and it is not considered wrong. Drawing of the mechanism. So we have that in the PowerPoint as well as in the recording. Calculation of the theoretical yield. Yeah, I'm really hoping it's bromobenzene. You will do that. Oh, it doesn't do anything. Okay. And then post-lab questions. Upload a picture of your drawing separation scheme for benzoic acid and the reaction mixture. I've given you a flow chart. Feel free to, do whatever you want there, but that's just an example. 3 significant peaks provided in the IR spectrum. Identify the bond in the carbonyl acid. Okay, I think I want to show you what the bond is. I did not, in case I didn't do that clearly. Let's go to the bond. Let's see if you can get the bonds here. So the 1700 is going to be the carbonyl stretch. That means the bond C double bond O is stretching. Okay, that's what it means. That's a carbonyl stretch. This is the hydroxyl stretch. So that means its oxygen-hydrogen bond is stretching. Remember, it absorbs the infrared light. It undergoes a change in amplitude or the change in bond length, and therefore a change in polarity. This one is a carbon-oxygen stretch. They're all stretches. None of them are bending. So they're all stretches. Okay, so that's it with your lab flow. So let me know if you have any questions. It's 100 points. You don't have a part B. You have a couple of Spartans, and this is what has happened. I have built the files and I have posted it in Canvas. However, I feel it's better I also email it to you. I forgot to email it, so I'll do it right after the pre-lab. Because sometimes Canvas does not know how to open the Spartan. So you may want to download it to your computer and then open it with Spartan. But this is what the question, this is how it's going to work this time. So let me see. I think this is my Canvas. I'm not sure. Okay. Okay, you have the instructions here, which is what I brought out. Now we will look at what you need to do. It's not difficult at all, and I've given you the files. I'm sure you'll manage just fine. But what I want you to do is compare the dipole moments for acetone and 2-methylpropene. So I've given you the file right there in the module. And let me just see if I can actually just open those. I'm sorry, I should have kept this open. So that was lesson 6. Okay, so you actually have this file and you can download it to your computer and open it and export it. So there is your acetone. It's already built. And there's your methylpropene. So what I like you to do is go to display, spreadsheet, and there are the dipole moments. I've already calculated it. So you'll take those values. Is the direction of the dipole moment the same in 2 molecules? So what you want to do now is just go to that file, and then if you want to see the direction of the dipole moment, go to display, properties, just select this. All right, that's all you need to do. Let me redo that. So you want to go to display, properties, just select this. Okay, you can close that, and you can see how in this acetone, you can see how the arrow points towards the oxygen. And then here, you don't see the arrow coming out, but that's your positive sign, which means the arrow is coming out towards this sp2 carbon. So it's already built and it's calculated. You should be able to handle this, I think. Let me know if you still would have questions. Is the magnitude of the dipole moment in acetone significantly larger than that of 2-methylpropene? So that has already been calculated. As I said, yes, it is. So this is actually your acetone. This is your 2-methylpropene. In case you're worried about which one it is, you can always just select that. That alone will stay. And then you can select the other one that will stay. Okay, so you will have that. And then let's just go to the second question. You want to compare the dipole moments in cyclohexanone and methylene cyclohexane. So I've also given you that file. So you should be able to see that. That's your cyclohexanone. This is your methylene cyclohexane. So what you do is go to display properties. You can display your vector. And then if you go to display spreadsheet, there's your, cyclohexanone and methylene cyclohexane. There are your dipole moments. So the calculations have been done. So it's fairly straightforward. You just have to answer the question. You're asked to obtain the dipole moment of perfluoroacetone, and that file should also be available for you. So let me open that, and that's what it is. So you want to calculate, it's no calculation. You just go to properties. You can display the vector, and there's your dipole moment. You can also go to display spreadsheet, and the dipole moment is right there. So there's no calculation per se. I've already calculated that. Okay, so it should be quite simple. I'm thinking what I like you to do is take these values and just analyze. That's all you have with one of them. And then I'm going to send you these definitely. And then you have a Spartan lesson 7. And again, I have the LUMO energies calculated. That is the lowest unoccupied molecular orbital. I have calculated these energies again. So if I go to lesson 7, I have that. And I can email all of these to you in case Canvas just creates a problem in opening it. So there are your 4 of them. So what you do is you go to display, spreadsheet. There are your LUMO energies. Okay, you'll have to explain why the arrangement is like that, whether it relates to what you learned in theory or not. I think that's all you have for that particular question. You only have one question. Okay, so take a look at this. Let me know if you have any questions. If not, all is well, I guess, and we can call it a day. And then if you have any questions, please stay back. I will turn off the recording and answer your questions. I'll get back to sharing in a minute.